Hello, my name is Mateusz Gołębiewski. I am a PhD student at the Adam Mickiewicz University in Poznań, Poland, and it is my great pleasure to be able to give a presentation on my research at this conference. The title of my speech is Control and Manipulation of Self-Images using Phase or Amplitude Change of Input Wavefronts and Potential Application in Magnonics. The subject of spin waves and their control in magnetic materials today covers a very wide spectrum of research, comprising a separate field, magnonics. The technological potential of signal transport without the emission of Joule-length heat, the length of spin waves from micrometers to tens of nanometers for frequencies from several to several hundred of gigahertz, the ability to control dispersion and group velocity of magnons, and of course high energy efficiency without compromising speed processing, makes them a very attractive successor to conventional electric current, among others in computing, memory, and various types of microwave systems. In this context, it's particularly interesting and advantageous to design magnonic systems where, thanks to static and dynamic factors, it is possible to control magnons and adjust their dynamic to set goals. In ferromagnetic materials, the dynamics of spin waves is determined by strong isotropic exchange interactions coexisting with anisotropic magnetostatic interactions. The issue of spin waves localization is one of the natural consequences of the development of nanoscale magnonic systems, their miniaturization, and attempts to manipulate the dynamics of magnetization. To keep order, I should now mention the dynamics of magnetization, which is the basis of my research. Of course, spin waves are precessional and coherent magnetization disturbances propagating without charge dislocation in magnetic materials, and the quasi-particle of spin waves is known as magnon, as visible in the GIF picture. Additionally, I have not included here a formula describing the change in magnetization as a function of position and time, known as the Landau-Lifshitz formula. The basis of my research on magnonic devices is the self-imaging of waves in their near diffraction field, known as a Talbot effect. The effect is a self-imaging phenomenon, as I said, resulting from passage of a plane wave through an array of periodically arranged opaque objects, or entering an array of single-mode waveguides into multi-mode waveguide, like in this case. This effect is characteristic to near diffraction field, and the reproductions of the periodic objects appear at the specific theoretically provided distances called the Talbot lengths. If the waveguide width is only a few times longer than the distance between apertures or sources, like in this case, the Talbot carpet is quickly transformed into a far diffraction field. But if we create the diffraction grating or array of sources much longer than the near diffraction field, create a complete Talbot carpets, and then we can use its properties. The Talbot length determines the period over which secondary beams refocus their source image. The software used to perform our simulations was MUMAX-free. It is a programming environment dedicated to conduct micromagnetic simulations, and one of its main advantages is using computing power from graphic cards. The feature allows to perform simulations up to 100 times faster compared to those carried out on CPUs. And thanks to this, advanced numerical simulations can be performed even on a relatively inexpensive GPU equipment. As I mentioned, in my simulations, I used a series of single-mode waveguides entering one multi-mode waveguide of a given width. I intend to use these systems not only to the self-imaging properties, but also the so-called multimode interference coexisting in the interaction of many wave modes resulting from single-mode beams bent at different angles. Matching of an input field with multimode waveguide mode fields leads to interesting effects. My model is pretty straightforward. Ferromagnetic film with thickness equal to 5 nanometers and an array of periodically arranged single-mode waveguides entering the multimode waveguide. The film has been uniformly magnetized out of plane, and the frequency of the induced waves is a bit high. It's 40 GHz, but I'm currently working on simulations with lower frequencies and a smaller field in plane. Here, however, the aim was mainly to demonstrate the applicability of self-imaging in magnonics. What's important, along the film edges there is no periodic boundary conditions. Spin waves have been continuously induced until reaching the resultant steady state. So yeah, from the viewpoint of practical application, the self-images generated near the source are the most promising. The effect of Gilbert damping is then the lowest. The first numerical tests were a comparison of the theoretical Talbot carpets near the first self-images, where the periodic boundary conditions were applied, with the results of numerical simulations, where PBC is no longer present. As can be seen from these examples, the results are satisfactory, and the Talbot effect is in the finite system is clearly visible. And here is an example for other parameters of the system, still showing compatibility. So it's just another example. Yeah. So finally, coming to the devices, the first proposition is a spin wave phase controller. When we are dealing with a series of periodically spaced spin wave sources, the Talbot effect can tell us about the degree of coherence of the source waves. When they are coherent, we will notice clear self-images at the distance equal to the Talbot length previously defined. When the coherence is disturbed, you can see the drastic disturbance of the Talbot carpet. By analyzing the intensity of spin waves at the expected reproduction distance, we're able to estimate the degree of decoherence. So the second main proposition is programmable spin wave logic gate. As I mentioned, the Talbot effect is sensitive to a change in any input source. However, using the property that Talbot length does not depend on amplitude or phase, we can always analyze the properties of self-images at the same distance and their change by manipulating these parameters at the input. Hence the idea of using interference and the Talbot effect to create a spin logic gate based on the phase or amplitude of the input waves. Yeah, and in the presented example, here we have 8 inputs, but we treat the 2 most distant from each other as an input signal, and the remaining ones as a control inputs. On the output, which will be the output waveguides, we will define 5 self-images by setting the appropriate thresholding, and by changing the phase or amplitude at the inputs, we obtain different amplitudes of self-images. And when we manipulate the phase on the inputs, for example, treating the pi radian phase shift as a logical 1 and no phase shift as a 0, we get the following truth table. And we get another one if we treat the logical 1 at the input with the amplitude equal to the control signal, and the 0 when its value is equal to 50%. These are, of course, only examples. There are many possibilities for encoding information here. We can also use, for example, the fact that Talbot length depends on the frequency, and thus the self-images appear at the different distances for different frequencies of spin waves. So you can create logical circuits analyzing many operations at the same time. And one more idea of using spin wave self-imaging is the use of multimode interference. I divided the simulation in the terms of 3 parameters: the distance between inputs, the number of input waveguides, and the width of the system. In the first case, we can see increasing the distance between sources. We can see that increasing the distance between sources is an analog of the diffraction grating constant. According to the theory, the self-images in the near diffraction field move away from each other, and the recreation of the entire near diffraction field in the far field also arises at longer distances. And in this example, I will also describe what is the key of the research. I as I explained at the beginning, the Talbot effect itself is here limited by finite width and appears only in a triangular small area that is hard to call a Talbot carpet. However, thanks to multi-mode interference, it is possible to reproduce this disturbance in a farther field. So we get a spin wave reproduction of a periodic objects from the inputs at a given distance from them. And this has a number of applications. So moving onto the second case, I increase the number of sources here to check the effect on the interference phenomena in the waveguide. So we can see here that with small number of inputs, self-imaging practically does not occur in the near field, while smeared beams from single waveguides create an interesting diffraction pattern. Yeah, here for a larger number of sources, we can already see clear self-imaging, and as in the above cases, but their number does not affect the distance at which the near-field reproduction is created. And the last case I analyzed was the increasing of the distance at which the near-field reproduction is created. The last case I analyzed was the increasing of the waveguide width, maintaining the number of inputs and the distance between the sources unchanged. Here, as it would be expected, self-imaging takes place in a similar way. However, the reproduction distance increases with increasing width. And of course, there are many technological difficulties in implementing the proposed systems. The most obvious is spin wave damping. So the Talbot effect analysis is limited only to the materials with a very low Gilbert constant, for example, yttrium ion garnet. Moreover, the presented devices were simulated for the frequency of 40 GHz and out-of-plane magnetization, which is certainly an additional problem. Nevertheless, I am still working on the implementation of similar systems also for in-plane magnetization with lower field value and frequency. Yeah. And in these studies, I showed that it is possible to demonstrate, use, and manipulate self-imaging in finite ferromagnetic systems. The Talbot effect is a promising phenomenon from the viewpoint of analysis, control, and manipulation of waves, which is why I believe that we will find a wide range of application in magnonics. The research is only in the design phase, but over the next year I expect the development of magnonic devices based on the Talbot effect, and hope that this work will help to understand its properties and great potential. And thank you for your attention.